Any words of wisdom before you start? Enjoy. No, for them, no. Enjoy too. Okay. Let's go ahead and get started. So, today you get to talk about mass spectrometry. I don't know if it's my first favorite or second favorite technique. It ranks right up there. It's an extremely powerful technique, and it really finds broad use in the food industry. And so these are some of the things that it does. Identify unknown components, and you'll see that it does it really well. It gives us a great deal of information and with very little material. So it really does a nice job in terms of unknown compounds. Quantify known compounds. And I'll kind of draw, or at least remind you of the importance of having mass spectral data on things that you're measuring. We can use gas chromatography, we get a peak. We can do LC, we get a peak. What's under that peak? You really don't know what that peak is. And if you measure it and it's not what you thought it was, you're in trouble. So the idea of making sure when you measure something by one of the other techniques it is what you think it is extremely important. It can also tell us a good deal about structure. You've got something that's completely unknown, you don't have any idea what it is. Again, looking at mass spectrometry can give you an identity, or it can just tell you what this is, what kind of a structure it is. So it's really a useful technique to us. Applications, it's kind of like gas chromatography. Many uses, just like LC. All three techniques. Exceedingly broad number of applications. It's so the idea of identifying, quantifying, such as steroids in athletes, monitoring the breath of patients by anesthesiologists during surgery to make sure that, okay, they're getting the right dosage of things, determine the composition of molecules found in space or someplace else, determine whether honey is adulterated with corn syrup, locate oil deposits by measuring petroleum precursors, monitor fermentation, look at dioxins and contaminated fish. You can go right on down the line. That's a small list. It's an amazing number of things where this technique is useful to us. Why is this usage so broad? Well, oftentimes we don't have a lot of material. And so we need to get as much structural information as we can with as little material as we have. When I'm working flavor area, I might have a microgram. I may have much less than a microgram of material. And that's what I'm going to have to do structural analysis on. Yeah. That doesn't work so well for many applications. So 10 to the minus 12 to 10 to the minus 15 grams. And I can get some structural information. I can get identity. And so, yep, sensitivity, very sensitive with structure. Specificity, again, you know what you're measuring. So what I'm going to do is I'm going to go through the parts of a mass spectrometer to give you an idea of what parts are here and how does this thing work. So that's what I'll spend probably most of this class time today, is going through this piece of equipment or instrumentation. And so these are essentially the parts. You've got to have some way to get your sample into this instrument. The instrument does operate under high vacuum, so you just kind of can't open the door and push it in. You've got to find a way to get the sample into the instrument that doesn't destroy your vacuum, that doesn't open up a hole, a doorway. So we have to have some kind of an inlet system. Then our source, that's kind of a broad term. That's really a source of electrical charge. It's some way to put an electrical charge on the material you want to analyze. And so this can be very commonly or easily just an electric filament. And so passive current through a metal, it'll give off electrons. Electrons, high energy, put a charge on my material. So it can be very simple and it can be very complicated. Again, I'll give you some good examples here. And so what I'm going to do is I'm going to blow this molecule up. I'm going to give it more energy. I'm going to put more energy into that molecule it could stand. It's going to blow into pieces. Okay, I'm interested in those pieces because the molecule will fragment where the weak spots are. It'll always fragment in the same way. So if I look at the pieces, it's like a puzzle. I can put them together, put these pieces together. I now know what I have. So this is my analyzer. Separates all those pieces for me. So I can look at one at a time, detect them. I need some way of detecting these ions, these bits and pieces. Then, of course, you get into data handling and drawing nice pictures for you. So those are pretty much the parts. Many different ways to do each of these parts. And so, like I say, I'm going to go through these parts and give you a little bit of background. Okay, the source. What I said, let's pass an electrical current through a filament. If we go ahead and do that, we get off high energy electrons. Okay, that's a simple way to do this. So, let's go back here, start with electron impact. Okay, pure compound is introduced into the MS. Different ways this can be done. And sometimes we just have kind of a two shut-off valves. And so I kind of open the shut-off valve, I push a nice tube in here that's a good tight fit. And I open up the second valve and push it in. I can simply put a probe, a metal probe, into the instrument. Okay, that metal probe has my sample on the end of it. It's in a high vacuum I hit with my electrons. So I can just introduce a sample directly into the instrument. No prior separation, nothing. If I got a sample, I can stick it into the system. Most commonly, though, we use either gas chromatography or liquid chromatography to actually introduce our sample. So now I'm taking my gas chromatograph. That's doing my separation for me. It's doing my isolation components. And I'm dumping whatever comes off the GC column into a mass spectrometer. So I'm using this for separation. The mass spectrometer doesn't like mixtures. It likes to have things kind of one compound at a time so it can sort out these pieces. So my GC does that separation of one compound from another. And the same for HPLC. So we've got techniques that feed the MS. And these are two of the major ones. Like I say, we feed those materials into a high energy area. We pass our energy, voltage, electrical current through this particular source. The source gives off electrons, 70 electron volts. That's what we adjust our energy for. So this molecule gets hit by electrons with 70 electron volts. It absorbs that energy and literally blows apart. Most of our chemical bonds are somewhere around 10 electron volts. So I'm putting 7 times what that molecule can possibly manage. So, like I say, it blows into pieces. This is a diagram of it. So this could be our gas chromatograph. Here are my molecules, hopefully separating, one by one, coming out into our system, coming out this way. Here's my filament down here, my electrical current gives off electrons of 70 electron volts. Basically, they bombard these molecules and blow them into pieces. Now it blows them into pieces that have no electrical charge. It blows that molecule into pieces that are positively charged and negatively charged. So my fragment's really a combination of no charge, positive or negative. And usually we set the instrument up so it's going to suck off. These are negatively charged, so my negatively charged plates here are attracting my positive fragments of the molecule. And so I'm dragging this out of here into the mass analyzer. So here's my source of energy, basically blowing things up and drawing them into the analyzer for separation. As I said, molecules fragment at their weak points, and they always fragment the same way. And so, okay, I get a bunch of fragments, I can look for it in a library. So I said we generate neutral, positive, negatively charged, generally measure positive, separate and measure each of these fragments, each of the pieces that it flew into. It's really a complex bunch of bits and pieces. The bigger the molecule, the more the pieces. And so we really get quite a nice complex pattern of like I say, fragments. But by measuring these, like I say, and recording them, we got great libraries. We can look up the pieces, the fragments of benzene. Okay, that's reproducible. I can look for that pattern. If I see that pattern, coming off my machine, I know it's benzene. So it's really quite a good system. But just some terminology that you keep in mind. We'll talk about two ions, two bits and pieces. How's that? My molecule just blew up. Talk about the parent ion, or I may talk about a molecular ion. They're really the same thing. Because I say they'll blow into pieces, but not all of them do. Maybe some portion of them just didn't absorb the energy in the same way or did fragment. And so we find we might have the molecule itself, intact molecule itself, that just has a positive charge. It's called the parent. It is our intact molecule with a positive charge. So parent ion or molecular ion. That's really nice because we're getting these because that is the molecular weight. After I know the molecular weight of a compound, I've narrowed it down to maybe 1 of 5 or 10,000 pieces, or 10,000 molecules. How's that? You might say, I think we've got a ways to go, Gary. But that's a good start. If I know molecular weight, I can rule out millions of other choices. And so it's a good start being able to identify the molecular weight of your compound. The base peak is now the most abundant fragment. Blows into many pieces, the most abundant one is called your base peak. And this tends to be counted in a little different way than most other. Because what it does, it looks at all your fragments, and that most abundant fragment is set at 100% of full scale on your recorder. Then there may be another peak that's 98% or 70% or 50%. So, you know, it isn't. It's like each fragment is some proportion of this base peak. So when you see the mass spectrum, you'll kind of get an appreciation for that. This is just a simple mass spectrum of carbon dioxide. And so what do we do if we bombard carbon dioxide? It's basically, here's our parent ion, that's CO2. There's 2 oxygens, 16 each, that's 32, and then the 12 here, 44. So we've got a parent ion of mass 44. Intact CO2 picked up a positive charge. That is your base peak. So that's 100%, that's maximum. Now, there's a fragment down here. So one of these pieces is a CO, carbon monoxide. And that has a mass of 28. And that can be maybe around 15%. So each of these fragments are relative to your most abundant fragment. So what pieces do I get? A mass of 44. A fragment of 28, I get a peak for oxygen, or 18, and a peak for carbon at 12. My pieces that I blew the CO2 into. The electron ionization, EI, electron ionization source, is really high energy. 70 electron volts, like I say, that blows a molecule into bits and pieces. And so there's advantages and disadvantages to hitting with high energy, blowing things apart. If you blow things apart, you got lots of pieces to put together. You have a lot of information. Oh, this little piece was there, that piece was there, that piece was there. And kind of try to put it together. And so if you get fragments, you've got a better chance of identifying because those fragments will be unique. One disadvantage is you may not see that parent peak. It might have just blown up and never have, you know, the intact molecule that's just blown into bits and pieces. And that does make it a little hard to identify. Like I say, if you know molecular weight, it's easier to do identification. So if you've got a molecule you don't see a parent ion, you'd like to. And it's not quite as sensitive. And the reason it's sensitive is you're measuring ions. That's what you're measuring when you start saying, what am I measuring? I'm measuring also the total ions that are eluting out of a gas chromatograph at that time. If there aren't many fragments, you don't get many ions, and your machine just kind of goes along. Okay, doesn't really give you a nice peak, which you'd like to see on your trace. So if you can blow them into pieces, you've got better sensitivity. If you don't, you lack sensitivity potentially. So this is an example of ephedrine. So that is a drug. And this is my electron impact So here we've got, our base peak up here. Base peak has a mass of 58. So this is the structure. So what it's measuring, this takes on a positive charge. That's the piece it breaks into. That is a mass of 58. That's almost all we see. There's a little bit of stuff in here. You can blow that up a little bit into pieces. But I don't see my intact molecule. If I've only got one fragment, one piece to look for, there's a lot of things that can have 58 as a component of it. So that's not really helpful to me in my identification. I don't have much information. We'd like to see it, the molecular weight is 165, so out there someplace, it'd be nice to see a molecular weight. You don't see it. So disadvantage here, we're not getting much information. So what do? We look at other ways to ionize, different ways to break those molecules apart or blow them up into fragments. Maybe we'll use something more gentle. Instead of having 70 electron volts, let's try and use a lower energy. So, okay, maybe I'll get to see my intact molecule. That'll help. Maybe I'll get to see some bigger fragments. Oh, that'll help me. So we start looking around for other ways to add energy to that molecule. In this case, we do it kind of second-hand in a sense. We have what we call a reagent gas, and we put energy onto that reagent gas, which it passes on to the molecules we want to measure. So instead of hitting something with 70 electron volts, we kind of ionize something else, and like I say, we ask that to go ahead and ionize our molecules. So reagent gas mixed with the sample becomes ionized. So these gases that we might use as a reagent gas, methane, isobutane, or ammonia are common. We can ionize them easily. They will transfer their energy to other molecules. This is very selective because now we're just not moving into bits and pieces. We're doing a little discrimination of actually what will fragment and what won't fragment into pieces. And we only get one ion, which is really nice because it gives us a molecular weight. So, okay, I get maybe a few more pieces out of things. Maybe I get a molecular weight. It helps me in looking for information. In some cases, having no fragments is a problem, but we get molecular weight. So it's kind of pros and cons. I get a molecular weight but not fragments. By electron impact, I get fragments but no molecular weight. So again, you try different approaches. What should I use? What gives me the best data? So this is now looking at ephedrine again. What did we see last time for ephedrine? We saw mass 58. That's all we saw. There wasn't anything up here. It's split into two small pieces. We didn't see them. But let's use a little less energy. We might be at 20 electron volts instead of 70. And so what do we find? Here's our mass. This says 186. Whoops. I can't read it. 166, I guess. Okay. And so we have a molecule. It's the mass plus one hydrogen. Hydrogen was what carried the energy over. And so it adds on to the molecule. So this has a mass of 166, the ion, but in fact the true compound was 185. So they picked up one hydrogen for energy. So, but we know that. So when it happens, we can say, okay, good, that's a mass of 165. It has a mass here at 148. So the idea that this is a pretty labile molecule up here, that hydroxy group will be lost. So this is the whole molecule. This is the fragment that occurs here. This is the fragment that occurs when this part of the molecule breaks. So again, we're looking at pieces and a more gentle way to look at them. Now we really have all kinds of different ways to do this. People are remarkably creative. Every time I get into a lecture like this, it reminds me of how ignorant I am. Because for my doctorate degree, I ran one of these for 3 years. And so I was in charge of operation, maintenance, and so on. And I looked at that instrument and I said, oh my God, what more could they give to this? Well, you know, I've got everything in the world I ever want. And this thing was, you know, kind of from here over to there, about that high, about that deep. And, it's like the Stone Age compared to where we are today. My ignorance is saying, what more could they do to us? They just continue to give us advances in this field. One of those is ways to ionize, but we also see ways to separate. And so, different ways to ionize: fast atom bombardment, impact of high velocity atoms on a sample dissolved in a liquid matrix. So we're going to go ahead and we're going to smack our target, a molecule we want with a high energy. It's going to blow into pieces just because of the energy of collision. Secondary ion mass spectrometry. Impact of high velocity ions on a thin film of sample on a metal substrate dissolved in a liquid matrix. Again, different combinations here. Nuclear fission fragments on the solid sample. Again, high energy photons. So we're bombarded with photons. Sometimes it's just energy, velocity of atoms. Sometimes you fragment by high energy light sources. Electric field, electrospray. Electrospray is becoming one of the most common techniques today, and we're going to go through that a little bit. Actually, you're going to get a different set of you're not getting a different set of notes. You're getting a set of notes that has two updated figures in it. How's that? Of how we're using electrospray in the work that we do in the lab. And there's also some techniques called DESI and DART. So anyway, there's just all kinds of ways to try and ionize these molecules. Put charges on them so we can do separation, identification. MALDI is one of them, matrix-assisted laser desorption. We were working with that, and when we first started on a particular project that we're working on. Application: high molecular weight analytes. So analysis of proteins, peptides, glycoproteins, oligosaccharides, oligonucleotides. And so large molecules, we kind of thought at one point that how are we going to get these things, actually, we got to get these ionized, then we got to have them pass through someplace, down the tube and do separation, be detected. That's a big molecule to get into flight and get going down some pathway. And this is really a neat technique. They found a way to get, we can easily do 5,000, probably get 10,000 molecular weight. So large molecules can be done in this manner. Again, one way we're using it for is determining if flavors react with proteins. One thing we've got today, we've got a trend for protein. Everybody wants more protein, especially plant proteins. They're viewed as being more healthy, more sustainable, and so on. But it's interesting, as we start putting more protein into our foods, we get rid of sugars, carbohydrates, starches, whatever. Well, we start putting more protein. Proteins are very chemically reactive. Our flavors are chemically reactive. And so we put flavor in, but the flavor chemically reacts with the protein and it goes away. You don't taste it anymore. And so if you think about some of these energy bars or high protein bars that you eat, they can be really good on day one. They can be halfway decent on week one. And they can get pretty ugly by the time you're talking about month 1, 2, or 3, or 4. What happened? High protein, we had great flavors in there at one time. They simply disappear over time. And the protein bars are really a nice example of that. But it's true of absolutely every food. We start putting more and more protein, we find more and more chemical reactions. And it's more difficult. People, unfortunately, eat what they like. And guess what? You can give all the health you want, say this is really healthy to you, but if they don't eat it, the person doesn't eat it, doesn't count towards nutrition. And so the idea, if we're going to supply nutrition, we're going to supply some component that's good for you, but it's not eaten, we're not getting anywhere. So it's really an important challenge that we're facing today. How we flavor and how we keep that flavor in food products. For the MALDI, like I say, that's what we started with in terms of looking into this task. We mix our sample in a highly absorbing matrix compound. That means energy absorbing. So we mix it with some compound that's really going to absorb energy. And then we hit it with a laser beam. So, okay, we've got this beautiful absorbing matrix with maybe our protein, whatever it is. We zap it with a laser. And basically, you can blow it up, put it into the environment. So we've got a high vacuum, give it a little bit of electrical charge, try and move it along through that vacuum. And we're going to go ahead and get this thing in flight so we can measure its mass. How big is that protein? What's its molecular weight? Can we identify that protein? And this is kind of the example. Here's our analyte. We put it into a matrix. With high energy photons, basically it explodes it. Some of these fragments are going to take on a charge, positive charge or negative charge, and we're going to be able to then move them down. And I'll show you how they get transferred, how we do the separation coming up. But it's really quite a fascinating technique. So here's just another configuration. Here's our sample matrix. We hit it with the laser. We'll have then these plates negatively charged. And so we're going to have positive, negative, no charge on ions. Negative charge is going to be drawn this way. They're going to get a velocity. The bigger the mass, the slower they travel. And so I can zap it, and then I can count the time for that to go from here to here. If it takes a long time before I get a signal, it's high molecular weight. The faster they travel, the smaller they are. So I'm really looking at zapping it, and how long does it take for these pieces to get down to the detector. Fascinating technique. It's really soft ionization tends to give us molecular weights of proteins or other components. And it does give us one charge per piece of sample, per molecule of sample. So it only gives us one charge. And that's kind of relevant because as I'm trying to draw these things up and get them moving down the road, they're big with only one positive charge. I have a heck of a time getting them up, getting them moving. So I can go up to maybe 5,000 to 10,000 mass and I can get them going. But if I want to look at beta-lactic globulin at 18,276, it doesn't go anywhere. So much for that one. And that's why we have to, again, other techniques. So one charge per unit mass. Limit molecular weight, and so that's our problem. So this is a protein analysis. Now, what the heck kind of protein is beats me. And so I didn't do it. I did take it though, come to think about it, out of the literature. So this is what the spectrum would look like. So we go ahead and we zap it. This is the matrix. So okay, we ionize some of that matrix too. So our matrix has a molecular weight, somewhere around 380 in this case. And then we don't see anything as we go up. Here's mass 2200, 400, 2466, and we get a beautiful, nice peak there. So what we were analyzing as a molecular weight, 2466.7. And that is our protein. So that took a certain amount of time to go down. By that time, I know it must have that mass. So that's one alternative, fast atom bombardment. It's somewhat similar to the MALDI, except with the MALDI, I smacked it with a nice laser beam. That's where my energy came from. In fast atom bombardment, I'm not hitting with a laser, I'm hitting with another molecule. And that's what transfers energy to the things I'm analyzing. And so, could be matrix of glycerol, nitrobenzene. My high energy comes from argon or xenon. So argon and xenon are what we bombard, and that's what carries the energy. Most of the energy goes to the matrix, exploding the matrix, but some of it does attach onto our analytes, and basically we get to measure them in the process. This is an example of this. It's similar to MALDI, just a little different. My atom beam is different. Instead of laser, light energy, what is it? It's our gases. So what was it, xenon, or where is xenon or argon. And so this is what's coming in high energy. Energy gets dissipated here, blows up. These are negatively charged, so any positive fragments basically get drawn up here at a certain velocity, which I measure. Anything that's neutral charge, anything that's negative charge, it just gets drawn away by the vacuum. It's under a high vacuum system. This is one of the more fun ones and shows creative on part of researchers. DESI, direct electrospray ionization. And so this is really neat in the sense that you have high energy here coming in. We're going to be putting electrical charge energy into a solvent, and that solvent collides with our sample. This is sitting out on a bench of atmospheric pressure, and by ricochets, it hits here, it blows your sample up to some extent. Some of those fragments then get drawn off by electrical charge, and this draws it into the mass spectrometer. So this operates at atmospheric pressure. This is an example. We want to look at pesticides on a tomato. What do? We take the tomato, we put it there. Here's our high energy beam coming in. It basically, anything that it strikes is going to take on some energy, and then it gets drawn down here. Talk about easy sampling. Take your tomato, put it under there. Oh, poof, I know what's on the surface of that tomato. So it's really neat in that sense. So DESI, that's a liquid. It's a solvent ionization that's been really put in high energy here. DART is when we do it with a dry, but it's exactly the same kind of thing. We put whatever we want here. We've got dry gas coming in at high energy, bounces off the surface, and we look for any fragments. Have you ever gone through the airport and somebody takes a swab of your briefcase or takes some money out and says, let me check your money? What are they doing? They're doing exactly that. They're swabbing the surface, they're holding it in a mass spectrometer. Okay. Are there any fragments that are characteristic of bombs or drugs or whatever else? Very quick. It takes them only a very short time to go and do exactly this. So like I say, lots of ways to go ahead and make a sample ionized to fragment it. Now we got to separate those ions. So I probably blew a molecule into 10, 50, 100,000 different pieces. Now I got to separate those pieces. I'm going to have to try and measure how much of each of those pieces we've got. So that's kind of the next part of the mass spectrometer. Did my ionization. Now let me separate that mixture. Historically, magnetic sectors were the first ways to separate. I think I'm going to go through each of these. We won't say any more than magnetic sector, quadrupole, ion trap, time of flight, and I put a question mark up. What's next? And I'm just so impressed that people keep on coming up with new things that people never thought of before. And so this is the magnetic sector. Like I say, this was one of the first mass spectrometers that were ever made. And what you've got is you've got your ion source here. You generate positive ions, negative, neutral. But you draw only the positive out. There's certain mass and a certain velocity. And somewhere there's a right-hand thumb rule about a magnetic field, a charge moving through an electric field, a charge moving through a magnetic field, there's a right-hand rule that says there's going to be a direction. And so as we have a very low magnetic field, we'll get molecules that don't have much velocity. Look at them coming around. Then we'll just kind of increase molecular weight. So different masses end up going and making it around the circle. And so they'll eventually, one by one, focus every mass down here to the detector. So we change the magnetic field, and we change then what ions make it around that pathway. It was a workhorse for many years, but magnetic fields are big, that's heavy, probably weighs 500 pounds. It takes a long time to charge that sucker up and to release it, and so it didn't take these measurements very rapidly. So neat, it worked, but it couldn't really get data very quickly. Okay, I got one check here, now I got another check, and so on. So they've been really replaced by other techniques. This was also one of the earliest means of detecting. And this is where you've got a sample here. We've got a sample one way or another that's coming in here. We zap it with high energy, so we make ions out of it. Then we've got electrical charge here, so we've got our charge being drawn out here given a velocity. And so we measure the time from giving it a zap here to the time it hits over here. Big molecules move slower, they don't get as much velocity. Small fragments, they move really fast. So zap it, and then I measure how long before I see it. Detect 1 mass, 2 masses, 3 masses, 4 masses, and so on the line. It's also an old technique, but it's really come back into favor just because we've gotten so good at timing things. Now we can look at what, 100th millionth of a second or something utterly ridiculous. We can detect time so easily now or so well today that this has now become a technique of choice again. And I'll explain why it's a technique of choice again, but that's really our advances in being able to time and accurately get a velocity of those masses. This is a quadrupole, and I put these next two into the magic category. In other words, I don't have the faintest idea how they work, but they do work. How's that? We've got we've got 4 of these down in my laboratory. And so what you get is a quadrupole, 4. There's 4 poles, 1, 2, 3, 4. And so here's our ions coming in here, our analytes coming here. We give it an electrical charge, blow it into pieces, and we channel then the positive ones to make it through these poles. These poles are varying in electrical magnetic charge. And so by doing things right, you can get a certain mass to make it through here, and hit this hole will be detected. Then change a little bit to the next mass that makes it through there. So basically, you're changing the electrical charge of fields on these poles, so we can get one mass after another that makes it down to the end. This is something similar in the sense that you take your ions and you form your ions again, and you're again looking at positive ions. This has the ability to store those ions. So what it will do is you will have everything set up in here properly so that we can be running some analytes into here, and it's going to blow that analyte into bits and pieces, but the charges, all of these pieces can be trapped here, and they can be then measured. So the deal is, on the other ones, in real time, I've only got so much coming in here, and I have to measure it. I can't store anything. I can't pull it all up, get a big bunch, and then look at it. In this one, you know what's coming through? We look. Here, I can keep on collecting sample until I pool all these ions together. Then I can measure them. So I can store, I can get much better sensitivity is the bottom line. So that's an extremely sensitive detector. So the ion detector, that's kind of that's almost the end of the road. It's the end of the road for the instrument itself, and then we get into electronics. But basically, we have to have some kind of detector. And so what we do is we're channeling charged molecules, bits and fragments of molecules, into a collision with a detector. And that detector is an electron multiplier. It gets hit by a charge, and it multiplies that. So it basically gives up maybe 10 ions. And that's focused on another plate. Oh, well, okay, I guess I don't have a picture of that. It gets focused on another plate, so those 10 get converted into 100. The 100 get into 1,000, and so I'm just multiplying the electrical charge, so I got something to measure. So extremely sensitive detector. That's basically what gives mass spectrometry its sensitivity. We're detecting charged particles. The charged particles hits a charged plate, it gives up some multiplication of signal. It's really a fascinating piece of equipment when all is said and done. So how do we use this, or what do we do with this? Well, identification. So here's just a really simple, is is there acetone in this sample? Is this a residue? In my business, we make flavors, we make essential oils, we extract the flavor, aroma out of plants, out of flowers, out of whatever for fragrance. We can use acetone for it. Acetone's a great solvent, but we don't want to leave any acetone in a nice floral scent of the food we eat. So we want to be able to say there's absolutely no residue of acetone. So what do? We take a bit of our sample, we put it into a mass spectrometer, the sample gets blown into bits, and I look for fragments that can only come from acetone. And so it doesn't care about all the rest of the things there. I'm keen to look just for a mass 15, a mass 27, 43, and 58. That pattern will always do the same for acetone. And you can program your machines and say, I don't give a rip about the rest. I want to know if this pattern is in here. And then I can say there is acetone in there, or there isn't acetone. These are low resolution instruments. You notice I put a number 15, 27, mass 43, mass 58. And you know that's not mass 58. You know, the only thing that has an even mass number is carbon. Everything else is going to be some decimal. And so this is what we call low resolution. That's 15 at mass 50 could be made up in different ways. It could be a hydrogen, a couple hydrogens, nitrogen. It could be a different combination of elements that would go ahead, or atoms I should say, that make up that mass. So we don't really know for sure what makes these up. But if we now have an instrument that measures that mass accurately, we can get a decimal to 3 decimal places. So that is at mass 28, it's 27.995. Now I know it can only come from a certain combination of atoms. I know what my molecule is made up of, what atoms. So it's called high resolution. And so here's nitrogen over here. That's 28.005 is the mass. So now we get an elemental formula. So I don't just get bits and pieces. I know this is made up of, C2H4, oxygen perhaps, whatever. I can give an elemental formula. It doesn't tell me how they're put together, but I've got an elemental formula. So life is getting even better in terms of identifying these pieces. Computer-assisted searching. That's always an interesting one. As we make instruments easier to use, they get more likely to be abused or to used without thought. How's that? I was in a meeting in California one time. I don't think I told you the story about this, but it was an American Chemical Society meeting, and the person was talking about identifying the flavor compounds in pineapple. So, done a nice distillation of pineapple, got pineapple juice, did a solvent extraction, concentrated it, put it through a GC, MS, and the machine looks, here comes a peak. Oh, I wonder what that peak is. The machines think about, look at the pieces. Oh, that's what those pieces are. Good. Okay, now it goes on to the next, peak as we're getting things coming out of a GC or out of an LC. And I'm sitting in the audience and this person saying, well, this is what I found in pineapple. I found this compound, that compound, here's normal butanol, and here comes ethyl acetate and ethyl butyrate, and here comes butanol, and here comes this. Okay, wait a minute now. He just said there's butanol twice. You can't separate normal butanol into 2 compounds. It's 1 compound. And so I was kind of looking at it in the order and saying, no, this isn't possible. It's absolutely impossible. And what he'd done is he fed the data into the machine, sampling the machine. The machine had given me best guesses. They were wrong. They were absolutely wrong. It was the best guess, but it wasn't the right guess on the part of the machine. And so, again, very politely, very quietly, how did you do that? How did you get 2 butanols? Well, maybe they can't be 2 butanols. Maybe one must be something else. Kind of stutters a little bit. What the danger is, though, that you get somebody operating the machine who doesn't know what they're doing. You know, the machine will give you its best guess. But there's some place in there for human thinking to intervene and say, no, I'm sorry, I want something else. And so the danger is when things get too easy, people use it without thinking about what they're getting. And they can be led astray. They can really be led astray. Wonderful technique, powerful technique, but it's not foolproof. The machine typically will give you some kind of a estimate of guess quality. My guess is really good, or the machine can say, my guess stinks, but you asked for some guesses, so here they are. And so that's helpful, but that still doesn't make it work out the way you'd hope. So anyway, we're going to call it quits at this point. Catch you next time. How's that? On Wednesday. Have a good afternoon.
Yeah.